Every year, the world recycles millions of tons of wood waste, and a large part of this trash gets a second life in the form of what we see every day at home, at work, or in stores. Particle board. Imagine this: mountains of wood chips, sawdust, and old furniture being transformed into smooth panels capable of holding weight, keeping their shape, and becoming the foundation of modern interiors. But how is a monolithic material with a perfect surface created from a chaotic pile of scraps? In this video, we'll show you every step, from metal separators that pull nails from the waste to giant presses with temperatures over 400 degrees. And if you watch until the end, you'll discover a secret that will change your perception of furniture. It all begins at a huge raw material yard, where the foundation for the future particle board arrives in a continuous stream. This is a place where the idea of rational resource use is brought to life on an impressive scale. Contrary to popular belief, high-quality commercial timber is almost never used for particle board production. Instead, the production philosophy is to give a second life to wood waste, turning what was previously considered a byproduct into a valuable material. Piles of raw material, reaching tens of feet high, are brought here. The base is technological chips, obtained from low-quality wood that is not suitable for lumber production. A huge share consists of waste from sawmills, slab wood, which is the side parts of a log with a rounded surface, board offcuts, and thin strips that remain after log cutting. Woodworking waste, such as shavings and sawdust, generated at furniture and carpentry factories during planing and milling, is also actively used. A separate and important direction is secondary wood. Old wooden pallets, crates, packaging, and even used furniture, after a thorough cleaning process, get a chance for a new life as part of a particle board. Every batch of incoming raw material undergoes strict incoming inspection, as purity is the key to quality. The first stage of cleaning is the removal of metal inclusions. Powerful electromagnetic separators, capable of pulling a steel bolt from a distance of several inches, sift through the stream of raw material, removing nails, staples, and any other metal fragments that could catastrophically damage the expensive shredding equipment. Next, the raw material passes through screening systems to remove mineral impurities, sand, stones, and other debris that act as an abrasive and quickly dull the cutting tools. If whole logs are used in production, for example, 20 feet long, they must pass through a debarking machine. In a huge rotating drum, or with the help of special cutters, the bark is removed from them. This step is critically important, as bark has a different structure, contains a lot of dirt, and significantly worsens the quality of wood chip bonding, as well as negatively affecting the appearance and strength of the final product. The prepared and cleaned wood begins its journey on a conveyor belt hundreds of feet long, which relentlessly carries it to the first stage of mechanical transformation. It disappears into the steel maw of a giant chipper, an industrial monster the size of a small room, capable of swallowing pieces of wood several feet thick. Inside this machine, with a deafening roar that makes the workshop floor tremble, a massive disc equipped with razor-sharp knives rotates. Rotating at a speed of thousands of revolutions per minute, these knives cut into the wood with incredible ease, turning whole pieces into a stream of uniform chips a few inches in size. But this material, despite its uniformity, is only a semi-finished product. The resulting chips are too large, coarse, and non-uniform in shape to create a quality particle board. Their cubic structure would not allow for the creation of a dense and monolithic structure. Therefore, the next step is a finer and more delicate secondary grinding, which takes place in specialized flakers or mills. It is here, in the hum of high-precision equipment, that the very particle that gave the final product its name is born. At this stage, the geometry of the chip becomes crucial, as it is designed with engineering precision. For the outer, face layers of the particle board, which will be responsible for its appearance and smoothness, very fine, thin, and flat flakes are needed. They are produced in knife ring flakers, which literally shave thin flakes from the chips, resembling flakes only a few hundredths of an inch thick. These flakes, having a large surface area, perfectly bond with the resin and form a flawlessly smooth surface, ready for further processing. In contrast, for the inner central layer of the board, which is its structural backbone, larger and thicker flakes are used. They create a strong internal frame that gives the particle board its final rigidity, bending strength, and the ability to securely hold fasteners, such as screws and bolts. The resulting chip mass has varying moisture content, which is unacceptable for quality bonding. Therefore, all the chips are sent to one of the most important stages, drying. Usually, huge drum dryers are used for this. The chips are continuously fed into a rotating drum, where they are blown with hot air or flue gases. The process is strictly controlled by automation. The final moisture content of the chips must be in a very narrow range, from 2 to 6%. If the chips are over-dried, they will not be properly saturated with glue. If they remain too moist, during hot pressing, the excess water vapor can rupture the board from the inside, forming defects. The dried chips are not uniform in size. To create the correct 3-layer structure of the board, they must be sorted. The chip mass passes through a system of mechanical screens or air separators. Heavier and larger chips, intended for the inner layer, settle first. The lighter and finer fraction for the outer layers flies further. This process allows for obtaining 2 or more streams of chips of different geometries, which will be used to form the sandwich of the future board. Now it's time for the key component that will turn the loose mass of chips into a monolithic board, the binder. Most often, these are synthetic resins, mainly urea formaldehyde or melamine urea formaldehyde. The sorted chips enter special continuous mixers. Inside them, the resin is sprayed through nozzles, creating a glue mist that evenly envelops each particle of wood. The dosage of the resin is critically important and is usually from 6% to 10% of the mass of dry chips. Along with the resin, other components may be added. The resinated chips, now sticky and ready for bonding, are finally ready to become a board. They are transported to a massive forming machine, where a continuous chip mat is born from the scattered particles. It is here that the engineering magic of creating a 3-layer structure takes place. The forming machine is a complex system that sequentially and with high precision sprinkles chips onto a moving conveyor belt. First, it creates a perfectly even bottom layer, using the smallest fraction of chips. Immediately after this, a much thicker middle layer, consisting of large and strong chips, is laid on this base. Finally, the entire mat is covered with another layer of the fine fraction, creating a mirror image of the bottom layer. This carefully designed structure, resembling a sandwich, provides the unique properties of the future board. Its smooth and dense outer layers are ideal for further sanding and laminating, while the strong inner layer gives the board the necessary rigidity and the ability to securely hold fasteners. The formed but still loose mat passes through a pre-press, where it is significantly compacted. This pre-pressing removes excess air from it and gives it a shape convenient for loading into the main press. This is the culmination of the entire technological process. The pre-pressed and cut into fragments of a given length mat is fed into a hot press. This can be either a giant multi-opening press of periodic action, which simultaneously compresses a whole stack of boards, or a modern continuous press of the belt type. Inside the press, the chip mass is simultaneously affected by 2 powerful factors. Huge pressure, reaching tens of kilograms per square centimeter, compresses the chips, leaving no voids between the particles. At the same time, the press platens, heated to a temperature of 400 degrees Fahrenheit, transfer their heat to the mat. This high temperature activates the resin, launching an irreversible polymerization process. The liquid glue instantly turns into an extremely hard and strong polymer, which permanently glues millions of wood particles together. The time spent in the press depends on the thickness of the board and usually lasts only a few minutes. During this short period, the loose mat turns into a hot, hard, and absolutely monolithic particle board. The hot boards after the press cannot be stacked immediately. They need to be cooled gradually to relieve internal thermal stresses and avoid further deformation or warping. For this, they are placed in special star or fan coolers, where they are blown with air for several hours until they are completely cooled and their structure is stabilized. The next step is calibration and sanding, which gives the board a marketable appearance. The boards pass through sanding machines with several heads, where wide abrasive belts remove a thin surface layer, bringing the board to a precise specified thickness and creating a perfectly smooth surface. At the final stage, the large technological boards are cut into standard commercial formats, and their edges are trimmed. The finished product undergoes strict quality control, where its density, bending strength, moisture content, surface quality, and dimensional accuracy are checked. Only quality boards are marked and sent to the warehouse. From there, their path lies to furniture factories, where they will be transformed into familiar household items, silently demonstrating the amazing journey from unnecessary chips to a functional and indispensable foundation of our comfort. Every year, thousands of tons of fiberglass rebar are produced worldwide, a material that's throwing down the gauntlet to steel. Imagine hundreds of spools of fiberglass, thinner than a human hair, merging into a single river, passing through sticky resin baths, red-hot dyes, and scorching ovens to be born as a rod that's 4 times lighter than steel, twice as strong, and completely immune to rust. This rebar is capable of doubling the lifespan of concrete structures and changing cities forever. But the most interesting part is hidden in the very heart of this process. If you watch until the end, you'll discover a secret that will completely change your understanding of the future of construction. It all begins at one end of a massive workshop, where a structure resembling a giant library for threads stands. This is called a creel. On a wall several yards high, hundreds, and sometimes even thousands, of huge bobbins are installed in neat rows. On each of them is wound the finest glass thread, or roving. This isn't the kind of glass that windows are made of. This is a special fiberglass, produced by melting glass and drawing it through microscopic holes. The result is threads thinner than a human hair, but with incredible tensile strength. These will be our skeleton, our internal army that will give the rod its insane strength. From each of these hundreds of spools, its own separate thread is drawn, and they all come together into one thick, fluffy strand. It's like thousands of small streams merging into one large river. This dry, white strand is the soul of the future rebar. Next, this river of fiberglass begins its journey. It passes through a system of guides and tensioning devices. This is a very important, though inconspicuous, stage. Every one of the thousands of threads must be tensioned with the same force. If one thread sags, while another is too tight, the load in the final product will be distributed unevenly, and it will lose its strength. Therefore, the machine carefully aligns them, preparing them for the most important moment: a baptism in resin. The dry glass strand is slowly submerged into a bath filled with a thick, sticky liquid, similar to honey or syrup. This is a polymer resin, our meat that will grow on the glass skeleton. It's a complex chemical cocktail. The base is usually a polyester, vinyl ester, or epoxy resin. A hardener is added to it, a catalyst that will trigger a chemical reaction and force the liquid to turn into a solid plastic. Various additives can also be added here. Pigments to add color, ultraviolet inhibitors so the rebar isn't afraid of sunlight, and flame retardants for fire resistance. The task of this bath is to saturate every single, even the tiniest fiber. The strand must be completely submerged in this resin so that no dry spots remain. The saturated strand, heavy with sticky resin, exits the bath and heads to its point of birth, the forming die. This is the heart of the whole process. Imagine a thick steel plate with a perfectly round polished hole, the diameter of which exactly matches the diameter of the future rod. The die is heated to a certain temperature. When the wet strand is pulled into this hole, several things happen at once. First, the die, like a press, squeezes out all the excess resin, leaving only the necessary amount. Second, it tightly compresses all the fiberglass strands together, forming a perfectly round rod. Third, the heat from the die initiates the initial stage of the chemical hardening reaction, or polymerization. The resin begins to transform from a liquid into a gel. At the exit of the die, we can already see the familiar shape of the rod, but it is still soft and vulnerable. But how does it get its famous ribbed surface to hold well in concrete? Immediately after exiting the die, while the rod is still hot and soft, a special strand of the same fiberglass is wound around it. A thin, resin-saturated thread is wound in a spiral on the surface of the rod, creating a relief pattern. Sometimes, for even better adhesion, fine quartz sand is sprinkled onto the sticky surface, which adheres permanently to the resin. Now, our rebar has not only strength, but also teeth with which it will hold onto the concrete. The formed and wrapped rod enters the longest part of the machine, the curing tunnel or polymerization oven. This is a long chamber that can extend for tens of feet, inside which a high temperature is maintained, usually 400 degrees Fahrenheit. Here, the final transformation takes place. This is not just drying. Under the influence of heat, the resin molecules begin to actively bond with each other, forming a strong, rigid three-dimensional network. The liquid, sticky syrup turns into an extremely strong and hard composite material that permanently binds millions of glass fibers into a single monolith. It's like baking a pie. As the rod slowly moves through this hot tunnel, it acquires its final, rock-solid hardness. But what pulls it through this entire long journey, from the spools to the oven? At the end of the line stands a special pulling device, which gives the whole process its name. Usually, it's two caterpillar-like mechanisms, similar to tank tracks, located one above the other. They gently but very firmly clamp the already finished hard rod with their rubber pads and pull it towards themselves at a constant, precisely calibrated speed. It is they that create the force that pulls the fiberglass through the resin bath, through the forming die, and through the oven. The speed of this movement is one of the most important parameters that controls the quality of the final product. And so, from the other end of this long conveyor, an endless, perfectly straight, hard and hot fiberglass rod emerges. The final cord is cutting. An automatic saw is installed across the line. It synchronizes with the speed of the rod's movement, at the right moment makes a quick forward motion, and with a sharp zzzt, cuts a piece of standard length, for example 20 or 40 feet, from the endless ribbon. Then it returns to its starting position, waiting for the next section to arrive. The finished, still warm rods roll onto a cooling table, and then they are collected into bundles, tied, and sent to the warehouse. And just like that, before our eyes, thousands of fragile glass threads and a barrel of sticky liquid, having passed through baths, presses, and ovens, have turned into a lightweight but incredibly strong building material of the future, ready to challenge rust and time in the concrete jungle. The fiberglass rebar market is not yet a giant like the steel market, but it's the coolest and most audacious newcomer at the party, rapidly gaining popularity. The global market for this material is already valued at hundreds of millions of dollars, and the forecasts are just insane. It's expected to grow by 10 or 12% annually. This means that more and more engineers and architects are looking at rusting steel and saying, "Dude, we can do better." And now for the main features that make steel rebar nervously smoke in the corner. The first and most obvious is weight. Fiberglass rebar is about 4 times lighter than steel of the same diameter. Sound boring? Now imagine this in real life. Imagine a truck carrying rebar to a construction site. It can bring 4 times more length of fiberglass rebar in one trip than steel, because it's limited by weight. Or for the same amount, it will take 4 times fewer trips, which saves fuel and time. On the site itself, 2 workers can easily carry whole coils or bundles of fiberglass rods, whereas moving steel requires a crane. This is a colossal saving in logistics and labor. Second is strength. And here, fiberglass just steps into the ring and knocks out steel in the first round. Its tensile strength is about twice as high as that of standard steel rebar. So you understand, to break a fiberglass rod, you need to apply twice as much effort as for a steel one of the same diameter. This means that in some structures, rebar of a smaller diameter can be used, saving even more weight and volume. It's like comparing a regular rope with a climbing rope. At a smaller thickness, it can withstand much greater loads. But the main trump card, the real superpower of fiberglass, is its war against rust. The main enemy of any reinforced concrete structure, from bridges to parking garages, is not the load. It's rust. Water and salts penetrate through micro cracks in the concrete, reach the steel rebar, and it begins to rust. The rust expands in volume and literally tears the concrete apart from the inside. Annually, the US spends billions of dollars on repairing bridges, parking garages, embankments, and tunnels destroyed by rebar corrosion. And fiberglass? It just laughs in the face of rust. It is chemically inert. It is completely indifferent to water, salt, acids, and alkalis. This means that the service life of the structure increases dramatically. A concrete structure reinforced with steel is designed for more than 50 years. And a structure with fiberglass rebar is easily designed for more than 100 years.